But ultimately, are you aware of this? Your flight through the air actually, your vertical, like gravity pulls down on you no matter what you're doing. Like if you just drop, you know this, if I drop this pen right here and just let it fall to the ground, and then I also took another pen and I threw it sideways at the same time, they're going to hit at the same time. Or gravity pulls on it no matter what happens to it horizontally. And so let's take a look at this. Did I say anything on here about on the note sheet about this?
Oh, that's probably what you're about to show.
Yeah,
Really shoot.
Yeah.
What are you thinking?
I'm pretty sure they did a Mythbusters. They shoot a bullet.
Oh yeah.
They drop a bullet.
Yes. Did they show it hit at the same time, or was it just close?
Yeah, close.
It's different trying to figure out where it's gonna land. It's obviously like camera on, hold the bullet at the same time. Really far away from the gun.
Right.
Yeah.
Well, basically what we're going to be doing is using this formula right here, because we actually know the acceleration of gravity. You've been using that in statics the whole time, which is entirely a function of the mass of the Earth. You understand that? If I was on the moon, it doesn't behave the same because it's not as gravitationally strong. If you were on the sun, aside from burning to death, you wouldn't jump near as far. So anyway, it's entirely based on that. So what do we know? Does it make sense that this would be the initial velocity in y and this would be the initial velocity in x? And that's the point. These two behave independently of each other. And this is, again, the vector idea that we looked at in math or in engineering 211. And so let's see. I could say then that and v of o is actually this entire vector. I mean, I could have put it at the end of the arrowhead, but it's the hypotenuse of that right triangle. So does it make sense to you that v of o in the y direction would be the actual velocity times the sine of 32 degrees? And that v initial velocity just in the x direction would be the same thing except with cosine? Now, by itself, that's not necessarily very helpful because I still don't know what the initial velocity is. So, but let's take a look at those equations. So given that this is the initial velocity, if you think about the equations you just had a second ago, isn't your position I feel like I need to change colors here. Your position in x is equal to your initial velocity times time. But let's build this a little more slowly. Think about the equation that we have. I'll just write it down here really quick. We have that position is equal to 1/2 at squared plus the initial velocity times time plus the initial position. But see, what we're going to do is consider that in x and in y separately. So let's do the vertical one first. So vertically, where am I vertically? So stare at this, picture and so forth. But vertically, then I would rewrite this as s of y equals 1/2 at squared plus v0 of y t plus s of 0 in the y location. Do I know any of those things?
Also velocity, initial velocity. Initial velocity 32 degrees.
Yeah,
And you also know that V of y is, would it be minus gravity or 9.8?
yeah. Don't we know that? Don't we know the gravity? Don't we know acceleration here? Because remember, as soon as we're flying through the air, there is an acceleration thanks to gravity. And so isn't that a 9.81? I think I'll leave the units off of this. Notice though, the distances are in feet. Does that matter? 4 feet, 12 feet? That does matter. Therefore, what mistake am I making? Nice job. 9.81 is meters per second squared. So what's the, is it 32.2?
2.2.
Can't remember if it's 32.2 or just 32. I think it's 32.2. Is that right?
32.185.
32.185. Okay, so it is 32.2. So you could round that however you want, but remember that's feet per second squared. And that's a constant, right? Because no matter what, that's happening. Never changes. It's always happening. Do I know anything else? I do know one more thing.
You know your initial time. Well, yeah, initial time would be 0, wouldn't it?
Yes, but I mean, I can say time is 0, but then I'm stuck on the jump and I'm not jumping. So I have to let time proceed. I have to let time go 1 second, 2 seconds, 3 seconds, so I can fly through the air. So I need t to stay a variable.
Would your S1 be your final position?
If you decide to make this the XY axis, and are you comfortable with the fact that you don't have to do that? You can actually put it any place you want. You could actually put the XY axis up there at point O, kind of origin. You could put it up there. I'm just going to stick it right there. But if I stick it right there, does it make sense my initial Y is 4 feet off the ground?
Yeah.
But it doesn't, as I said, it doesn't have to be. You could actually put the XY axis up there at the start of your jump. That'd be okay too. But just since the graph shows this way, I'll go ahead and leave it that way. So just to make clear that that's what I've done, I'm going to call this X and this Y. So it's clear that's the origin. So in a sense, I'm giving credit to the landing spot. I'm saying, you know, the landing spot will be Y is 0. So Y is 0 means I landed. And so that's the advantage of doing what I'm doing here. And so now it's kind of cool because now I have a formula for my initial or for my position in Y. Now remember that position in Y is a variable. It's changing, right? As time changes, my position in Y changes. Notice in the picture, it's clear that my height is going to grow beyond 4 feet for a while, reach some maximum height, and then it's going to turn around and come back down and actually land at -4. But do you see why T is a variable? So time lets me fly through the air. And when I do that, my Y height changes too. So those are variables, whereas the other stuff is kind of fixed. And then notice, unfortunately, this initial velocity isn't a known quantity. And so, you know, it's kind of a bummer again. So the way I look at this from a recipe perspective is this is a cool equation, but it's still got 3 unknowns in it. So it's not all that useful, but it's like, I don't know, maybe that'll be worth something. Maybe I can use that for something. I don't know. Whatever. Let's see. Let's go down and play the vertical or the horizontal game now. What would this equation look like if I did it horizontally though? And I said, okay, what about your position in the X direction? Well, notice it's the exact same formula, except for now we're talking about only what's happening in X. What do I know about this? You do know your initial position, which is what in X? 0.
Your initial axis. Acceleration. Well,
Yeah, now what's the acceleration? This is an interesting one that isn't obvious. What's your acceleration if you jump your bike? You're pedaling along, you know, maybe, or you're hitting the brakes. Like when you're on the trail, you can hit your brakes and decelerate. You can pedal and accelerate. But what happens once you leave the jump? It's constant. And it's actually not just constant. It's nothing. Is there anything slowing you down or speeding you up? You could argue, good job. You could argue that air resistance is having some impact on your speed, right? But given that you're in the air for a really short period of time and you maybe annoyingly saw that in physics all the time, assume air resistance doesn't, it's like, well, it does matter actually. So, but it actually matters very much dependent on how long you spend there. Does that make sense? And in our case, we are spending so little time that I would say it could be negligible. And by the way, did you notice where I decided to try to land? You see, I'm safely past the lip. In other words, if I screw up a little bit, I'm still okay. So if the wind blows me back 6 inches or whatever, I got a little bit of cushion. But what I don't want to do is land way down the hill because I'm going to crash more. And you can also appreciate if I flew way down the hill, I'm going to hit the ground harder. We'll talk about impact later in this class. And if you hit hard enough, and I've done this, your forks compress and then you bounce back up and fly up in the air and then crash anyway. So interestingly, the acceleration in the X direction is actually nothing. In other words, what that's saying is whatever speed you left the ground at horizontally, that's going to be the speed you land at. Your speed does not change. The other thing to point out that's just kind of cool is, did you notice originally this equation up here had the initial velocity in y, and this had the initial velocity in the x, two different variables, whereas now they're identical. So like these two equations can talk to each other a little bit now. Does that make sense? They got some stuff in common. They got t in common, and now they got v0 in common. But notice they don't have these in common because those are two different things. They're position, but one is x, one is y. So these two can't talk to each other, but the other ones can. So again, I maybe somewhat unsatisfyingly don't have everything I'd like to know. But I got some cool stuff now. So I'm kind of thinking maybe I should rewrite these to clean them up a little bit. But so this equation then would be S of x equals, that whole first term is gone, and you have v0. I'm going to put t over here.
Would it be smart to solve for velocity on the position of x and then plug it into the vertical equation? Would that make it more complex?
That's a great question. I mean, and that's the whole point. Like, you notice I kind of haven't even really read the question yet. I don't even know what I'm calculating. I'm just saying, hey, I got some equations of motion, and maybe I should be doing something with them. So I like what you're saying, because you're basically saying, should I mess with these a little bit? Should I play around with these equations? Should I try to put them together in some way just because I can and maybe make something that's useful? The answer in a sense is kind of like, yeah. Like, does that hurt anything? No. Would it help? I don't know. Maybe it helps, maybe it doesn't. But that's my point, is that's how you're good at physics, if you or get it to be not confusing, if you just kind of stare at this and say, well, what could I do? Now, do you understand that, in a sense, if I knew my initial velocity, I could plug that in as a constant. And then I could plug in any time I wanted to know kind of exactly where I was. But remember, my overall goal here, what am I asking? Find this initial velocity. And the limiting factor that I have is I want to land right there. Does that make sense? Because I know where I'd like to land, and then I'm working backwards to think, what would my initial velocity be? So I don't know, what could I do with this algebraically? So do you agree that those two kind of clouded equations are models for any place you are between takeoff and landing, between O and L? But now let's kind of overtly talk about L. Like, I want to land there. Do I know anything about what there is? Don't I know then that S of x is 12? In other words, remember, S of x is a variable. It's anywhere from 0 to 12, but at L, I actually know S of x is 12, don't I? So then I could say 12 equals V0t cosine of 32 for what that's worth. But again, that's not very satisfying, right? Because I don't know, like there's two unknowns in it, right? So it's like, man, that's not so great. But it's true. What about the other equation? Do I know anything about that? What do I know? S of y would be 0. My height is 0. So and also somewhat unsatisfying equation because it also has two unknowns in it. But what's cool about them viewed together? I have two equations, two unknowns, which means that's actually solvable. There's one answer to that. And so I'm going to know the time and the initial velocity kind of simultaneously here. Hey, that's kind of rad, right? Is that kind of cool? This is actually the typical physics problem. They tell you the initial velocity and just kind of say, where are you going to land? Does it make sense that if I'm a mountain biker, that's not the best question? It's like, well, I think I'll just jump at 15 miles an hour and I wonder where I'll land. Really, it's kind of like, no, I know where I'd like to land. I wonder, it's like, let's work backwards. This is a cooler problem. Of course, you could, guess and check your way, like try 16 miles an hour, put it in there and say, oop, lands in the trees. Okay, well, let's try 12 miles an hour. Just keep guessing until you land in the vicinity of where you wanted, which, by the way, there's nothing wrong with that. But if I solve that system now, of course, it's just interesting to think, I wonder if I could solve that, algebraically or whatever. But remember, what is an engineer going to do once they get to this point? They're going to stick this in the matrix. They're going to stick it in Desmos and just see where they intersect, because you don't want to screw this thing up. This is pretty solvable. But it might be like the top equation, I could solve it for t and then plug t in down below. Or I could solve the top one for V0 and plug V0 in down below. This one is actually pretty algebraically solvable, I think, because I've got to let you guys out of here at 12:30 because you need a break between classes. But I think I'm just going to tell you the answer to this.
Divide 12 by cosine 32 and grab that whole left side, plug it into the second equation, and you initial position with time, and then with the second one time squared. You solve it for time itself, and then it'll give you only time, and then you go to your initial one, your original the first equation, plug in for time, since there's only solve for initial velocity. Yeah. Trying to get rid of.
I will tell you, just if you're enough of a mathematician that me just writing the answers up there kind of bothers you. It's kind of like, I mean, maybe not bothers you, but it's like, this is kind of, it's kind of fun. It's fun to be able to see if you can figure stuff out yourself and all that. I will say that if you took the top equation and solved it for V0 and then plug V0, take this expression right here, and just plug it in right there. Maybe you can see that'll leave a squared equation, and then you use the quadratic formula to solve that, and you'll get two answers. Why would you get two answers? Because if you went back in time, does it make sense? If you went back in time, there was a point earlier that didn't exist in the real world because of the jumps and so forth, but there is two places that parabola would have hit that x-axis, right? So one of them will give you a negative time, which will be kind of like, oh, that never happened. The other one will give you the time of 0.845 seconds, and then you can plug that time into either one of the equations to actually get that velocity. And so notice that's amazing now, because I took all these measurements and I can say, sweet, if I set my speedometer to 17 feet per second and I go off that jump, I'm going to land where I want to land. Like, I don't even have to wonder. That's just rad. The biggest jump I have went off so far falls just like this one. It's almost identical to that, coincidentally, except I'd say it's further. It's probably more like 18 feet. but but it has a huge ditch in it. And then this part right here is more like a wall, like it's kind of like this. Like if you hit here, you would just get thundered. And I was out there with the kid and he's like, I'll tow you in is the language of mountain biking. He's like, I'll tow you in, which basically means he's done it before. If I go the speed he goes, it'll be fine. And so I did that jump with kind of his help. But it's kind of cool to think that you could actually make these calculations and pull this off. So interesting. And then notice you have 1 second, like less than 1 second. I'm actually really happy with that because that gives me far less time to kind of do what mountain bikers call the dead sailor program, where you just kind of sit there and begin rotating. And that's actually hard not to do if you're in the air very long. So I have less than a second to kind of screw that up. What about the second question? What angle and velocity does he land? Why would I care about that? You actually do care about velocity because, and not just out of curiosity, but there could be another turn coming up or something of that nature, in which case, because you don't have any control over that, right? As soon as you leave the jump, you're just going some speed. And the other part of it is that velocity could cause you to kind of compress into the ground enough that it made you crash. And then angle's a part of that too. As I said a minute ago, does it make sense if you have a hill like this and you kind of land in that direction, you're going to squash more than if you come in and kind of land a little more parallel to it. You're not going to have to absorb near as much of a hit, basically because of vectors. I mean, look at the vector of this. That's the vector going into the ground, which isn't very long, whereas this vector is really long. So the amount of force going directly into the ground, which is what's going to make you crash, is not near as much. And so what angle am I heading in at? Turns out to actually be really kind of cool to calculate and important. How would I do that? Or do I know anything that would help me do that?
Oh, you already know V of Y and V of X when you plug in the initial position. And the angle, the tangent of angle of the rise of the run.
Yeah, don't you have this calculus derived velocity equation right here? So we either could take our position equations that we just made and take their derivatives. In other words, replace S with, is that right? I'm saying that wrong. Yeah. Velocity is ds dt, isn't it? So I could take the derivative of S, making it ds dt, take the derivative of the other side, and it's going to create this equation here. So I could just do it with calculus and the equations on the other page, or just make them myself. I think for the fun of it, because it's kind of quick, I'll just make them. We said proceeding. We said the other day, proceeding from here to here is a derivative. And again, that's because you're saying, hey, how is S changing? I know S, but I'd like to know ds dt. How is my position changing over time? Oh, that's velocity. So do you see the logic in that? So I'm going to do it sort of manually here because it's kind of fast. So let's take that dsy equation up there. So let's see, ds dt. And I think I'll just write the y over here. Like this is the vertical, or the vertical version. Maybe I should write vertical. So you think, what's the derivative? What's the derivative of that? So derivative of 16.1 t squared, doesn't the 2 multiplied by 16.1, which gives you 32.2, and then the t squared reduces to t. And then v0t, the derivative of that is just v0. Isn't that what the equation said on the other page? The velocity is equal to the acceleration times time plus the initial velocity. Wasn't that the equation on the other page? Kind of cool, right? So I don't care kind of which way you do it, but Remember, it took us calculus to make those equations yesterday, so that's kind of cool. So there's the vertical equation, which basically means now I know my velocity, don't I? I've now a formula, I've made a tool for myself that will tell me my velocity anytime I want to know it. Let's see. And then for the horizontal version, I'm sorry?
Sine 32 still on the view or
Yes, I lost my sine 32, didn't I? Shouldn't it be there? Everybody agree with that? Basically, I got to staring at this V0t here and sort of forgot there was another constant on the end of that. So, and then of course the derivative 4 is nothing, right? So that's still sitting there. And by the way, remember that makes V0 sine of 32 is V0 of y, right? And then if I take the derivative of our second equation, the derivative of s of x would be, again, ds dt. Which will then become the velocity in the x direction. The derivative of v0t cosine of 32 is just v0 cosine of 32. Because the acceleration is nothing. So just to give you time to think about this, does it make sense? It's this equation, but the acceleration is nothing, which basically just leaves your initial velocity, and that's what our equation is, right? So I could have just used those two formulas. In a sense, I would recommend you just use those formulas on your next test. Don't necessarily think calculus. So don't I now have equations for my different velocities? But do I know anything? Again, recipe, I've got Vy and V of X. Do I know anything over there? I know everything. At landing, I know T and I know V0. Don't I? Didn't I just figure those out? So I know T is 0.845 seconds. I know V0 is 16.7 feet per second. So can I find my, well, notice I have velocity of y and velocity of x, whatever that means. Again, just to save time, velocity of x works out to be 14.2 feet per second. Velocity of y works out to be negative 18.4 feet per second. Why is it negative? Because you're falling. So your x is still positive. Basically, you left the jump at 16.7, but horizontally that reduced, that got modified down to 14.2, and you stay 14.2, again, minus one resistance. But your y velocity is constantly changing. And so notice you're actually going faster when you hit the ground than when you left the jump. That's because you fell through the air pretty far. Gravity had a lot of time to work on you, and so you started really speeding up. Interestingly, if you were to kind of make a vector out of that, this is v of x, and this is v of y, then wouldn't this actually be your actual velocity, kind of the speedometer version of your velocity? In a sense, you could say I'm done. I know the x and the y coordinate of my velocity, and I'm done. But I could also do the Pythagorean theorem and figure out what your actual velocity is. Again, that could be like, ooh, that's not good. I'm going way too fast. I'm going to crash. I can't even ride my bike that fast. I'm just going to wobble and crash. And notice you could even find, as I said up here, what angle does he land at? What angle does he land? And so I don't know what to, I mean, I could call it that right there. So I could say the tangent of theta is equal to opposite over adjacent. Notice I took the negative sign off of that because I drew a picture showing me this. And so theta belongs in the picture. So I'm using positive numbers for that. And that gives me 52 degrees if I go inverse tangent of that, approximately 52 degrees. I won't take the time to do this, but basically that means this angle right here is 52 degrees. Does that make sense? But what I need to know is what angle did I land at? Because what I'd really like to know is what's the angle between my path and the ground, because that's what's going to cause me the problems. But at least I understand kind of relative to the ground, I'm basically going 52 degrees down relative to the ground.
That's the angle of the ground.
Yeah, that's right. And the ground's not level there. So in a sense, that's only marginally meaningful. I will say if we went on, the derivative of an equation tells you the slope, doesn't it? So if I was able to find the parabolic equation for that and take its derivative, which we kind of did in the basketball hoop problem back in my calculus class, but if you found the equation for that parabola, which isn't terribly hard to do, and then took its derivative when x is 12 and y equals 0, we took its derivative there, then we would know its slope. And so we could find the angle of the dotted path. And now we have the angle of the ground, and we could actually see what the angle, kind of this sliver of an angle is right there. Because when that angle's small, you're not even going to feel it when you land. That's what's kind of cool. This is neat, and you're absolutely going to see kind of a nice clean question of this type on the test at some point down the road. But knowing how stuff flies through the air is really cool. I wouldn't call that a tremendously typical engineering application, because you're just like, when are you engineering stuff that flies through the air? You kind of don't like stuff to do that too much, but you can appreciate with respect to an airplane. You're applying, force to it, because the difference between a bike and an airplane is when you're in the air, you actually can change your speed, right? Because you got a motor and a propeller and stuff. So maybe an aeronautical engineer would be a little more interested in this than a kind of a mechanical engineer would be. But this is powerful. So like pour over this on your own time and make sure you kind of feel good about it. Do you notice how impossible this set of questions is, though? If you want to learn it as step 1, step 2, step 3. Do you see how I was able to build it just with 2 equations that we already used last time? And I didn't really have to know anything other than just plug in stuff that I know. And maybe there's a few things that aren't obvious, like, oh yeah, your horizontal acceleration would be 0 because there's nothing propelling you along. But I just used algebra skills to figure stuff out, and I didn't exactly know what I was doing. I just plugged in things that I knew and just looked to see if I could kind of find my way out of the fog. That's a great way to think about this. And that is the difference, as I've been saying, between, what I felt like as a freshman in physics of calculus at U of O and kind of how I think about it now, because I'm just better at math than I was then. In a sense, that's 12.6. I forgot what the actual title of the section is, but it's either parabolic motion or quadratic motion or something like that. So yesterday or Tuesday, we went in a straight line, and now we're saying what happens if we kind of fly through the air. And then 12.7 is saying, what if you just drive in some curved sort of manner, where you're at the skate park and you just go down a curve that levels out or something, that isn't even defined. Just some concrete worker was like, and just made some curve that has no definition to it, really. What if you're controlled by, that, a ramp or something, or you're driving and you just turn left and turn right and curve all over the place. That's really what 12.7 is getting at. So let's take a look at an application there. Let's see, is this the next thing I want to do? Actually, I want to stare at this one for a second. So let's look at this one. So notice this, and again, this is a typical book problem, because what's going down the ramp? A box. Wow. These problems are so much more interesting if you just put like a guy on a snowboard, then all of a sudden it seems like it's worth doing. But if it's some stupid box sliding down a ramp. What do you notice about the ramp, though? What kind of a ramp is that? Notice it's a parabolic ramp. It's not free form. So at least let's think of this as a skateboard. it's not a free-form shape, it's a parabola. And I don't know if you can appreciate this, but to actually design a parabolic ramp and say, okay, concrete worker, go make that, that'd be really hard. If you just let them kind of make a curve, then it's going to be fine. But that's kind of weird. But remember, those two formulas I showed you earlier required us to be able to take a derivative and stuff. And so you actually wouldn't be able to do the problem if you didn't have a sense of, like what that equation was. Side note, if you just walked up to a skate park and took some measurements, would you be able to do regression and actually come up with some kind of an equation that was roughly equivalent to it? It's kind of powerful, but yeah, you actually could. So let me give you a little introduction to the thinking here, so you at least understand what's going on with this before we tackle this problem. So let me just start with a blank piece of paper. I guess I'll say 12.7. Instead of projectile, that's the word I was looking for. 12.6 was projectile motion, projectile flying through the air. This is really just generic curved motion. So let me just say this. If I draw just kind of a random curve like this, like somebody's driving and so forth, and let's just put you here, you're here, and you're kind of, we'll say you're traveling in this direction along that path. Here's the thing that you got to understand about this section. If I take off, you still have velocity, just like you would in a car if you're in the curves, right? But the weird thing is velocity's kind of got a direction to it. Does it make sense? That's your actual velocity. Notice it's not even pointed along the road you're on. I mean, if you're in your car and you have cruise control set and you're going 50 miles an hour and you go around a curve, does it make sense in any moment in time, wherever your car is facing, that's the direction that you're going 50 miles an hour? Now you might choose to say, I don't want to go that direction anymore, but your speed is defined as what direction are you pointing at that moment. Now, 2 seconds later, it's going to be pointing a different direction. Does that make sense? Like back here, if you were on cruise control, then your velocity was pointing over there. Does that make sense? So I'd like that to feel good to you, I guess, that's what velocity has to be. And that might have some overlap, like you might have discussed that. You might have discussed this in regular physics class. But what else is going on with this? Can you also be accelerating or decelerating? Remember, when you say accelerate, you're always thinking of speeding up, but there's negative acceleration, or sometimes called deceleration. And you might be doing that in this corner, right? So could you still do that? Yes. And that is in the same exact direction, and because you're actually changing your velocity. Acceleration was a change of velocity. You're changing it, but unfortunately, there's two accelerations now. This one is called acceleration tangential. Tangential acceleration. And of course, the word tangent, I hope, stands out to you as kind of like, yeah, that's in the same direction as the velocity because I'm just changing my speed. And so I can be hitting the brakes or I can be hitting the gas as I go around a corner. If I hit the gas, then that vector length of velocity is going to get longer because I'm hitting the gas and speeding up. And so that's tangential. It's going in the same direction. But there's also another acceleration perpendicular to that. Called normal. What's normal code for? Right angle. So in strength of materials, we're going to have normal forces pushing down on things all the time. So it's normal because it's perpendicular. Now that seems kind of weird. Does that bother you? It should bother you some. Like, isn't acceleration like feet per second squared? And so like, what is that? What is that actually doing? Let me go back here. But here's one thing. How did I know where to go? Like, how come acceleration normal is not up there? Because it actually isn't up there.
You're turning in that direction.
Where is it over here? It's actually here. Basically, it's always perpendicular, but it's perpendicular toward the inside of the turn. And in a sense, this is what people call centripetal acceleration. So it's like if I'm in my car and I decide to hang a left, your body doesn't want to hang a left, right? So the car's like, okay, I'll go that way. And your body's like, no, I want to go that way, right? And so you feel the effect of slamming into the door on the right side, so to speak, or you can shift to the right. If you're turning left, then you're going to go this direction. And so basically what's happening is if I'm turning left like this, basically the door is over there kind of going, you have to go that way. You're going to get shoved toward the center of the circle. Does that make sense? Because your vehicle, if you will, is going around the corner. So here's the important thing to understand about these. This acceleration is actually a change of your velocity. In other words, you are pushing the gas or the brake. That's normal. That's what we've been talking. That's what we've been doing all this time. That's what acceleration has been. However, when you're turning, normal acceleration is actually a change of direction. So it actually doesn't change your speed at all. And it personally bothers me a little bit, really not having a huge physics background, that this is even called acceleration. It almost seems like it should have a different name. Like, why is that called acceleration? It just feels like acceleration is speed change. This is a direction change. And so do you see why it has to point into the circle? Because in a sense, that's what's going to cause this V, if you will, down here to be pointing in another direction, because it's getting pulled in this direction by that acceleration normal.
Make the normal acceleration 0 and still take a turn, or will it always be present?
If the acceleration normal is 0, then you're not turning. That's exactly right. If AN is equal to 0, then you're going straight right now. Now, collectively, and this bothers me even more, but I'll go ahead and say it because I can't remember if it comes up in one of your assignments, but if I was to kind of take that right hand one and say, okay, this is my acceleration tangential, and this kind of short was my acceleration normal. What's your actual acceleration then? Well, you may remember from last term, if you draw vectors head to tail, if I took that AN vector and moved it over to here, then collectively, that's actually your acceleration overall, which is sort of a combination of your speed change and your direction change, which again, I kind of don't like because now it's sort of a meaningless number. But notice the Pythagorean theorem, like I could Pythagorean theorem those two numbers, AT and AN, and then I would actually just have an acceleration. So in the event that you look in the back of the book and the answer is not right, it says the acceleration is this, if it just said what is the acceleration without saying what is the acceleration normal and what is the acceleration tangent. By the way, on a test, I'm probably going to ask it that way. I'm going to say, what's the tangential and normal acceleration in this situation? And then you're done. But if you did Pythagorean theorem those two numbers, you would get one number for acceleration. It just doesn't feel very meaningful anymore. I don't find myself wanting to separate those. I'm at least okay with the fact that acceleration normal is a change of direction, normal to the tangential acceleration. I'm okay with that. It's what's making me turn. So there's not just speed change, there's direction change, and that is defined as acceleration. Extra credit, why is that defined as acceleration? Like, it's sort of occurring to me as I'm standing here talking, like, there's probably a good reason, right? That they could have made up a totally different name than acceleration for it. But there's probably a good reason for that. I wonder what it is. I don't think I know what it is. So since I'm here, maybe I'll say that A could be found by taking the square root of AT squared plus AN squared. Now, be staring at these two formulas because let's see if we can use these now. So notice this acceleration right here, that's actually telling you A of n, the normal. And notice, and it's kind of interesting, what does that recipe call for? Like if you want to know how much change of direction, kind of force, if you will, is on you, notice it's a function of v and rho. Why would that be a function of v and rho? Think about driving a car. Rho is the radius, remember? So it's like I'm going around a corner.
Isn't it pointing towards the center of that radius? Or
It's pointed, exactly, it's pointed towards the center of that radius circle right there. But doesn't the velocity make a big difference? When you're going around a corner, if you go super fast, don't you kind of almost want to slide off the road? So velocity would have a big effect on how hard you have to turn to kind of get yourself to go that direction. And then the radius, of course, if the radius is really sharp and you go really fast, you're probably not going to get the job done, right? You're gonna crash into the guardrail. So doesn't it kind of make sense that that arrow that points toward the middle of the circle is affected by velocity and radius of the turn that you're on? That's kind of cool, isn't it? Again, it feels rather magical. It's like, well, why do you divide them? Why is the velocity squared? Where did all that stuff come from? Well, I'll post that if you want to look into it a little bit. But let's just say, okay, great. If you want to know the normal acceleration, there's your recipe. And then if you want to know the radius, which the rho radius, then we got to take a bunch of derivatives. And again, hey, the equation of that skateboard we just looked at a second ago happened to be an equation, and it wasn't terrible to take its derivative and second derivative. So I could actually find the radius that was on. So let's go take a look at that. So be staring at those two formulas. Notice the box has a location right now, because remember where you are, and we just looked at this in the notes, like where you are is totally determined by, totally determines the size of the circle you're on. So we're over there at 2 meters right now. And so that's where we are. Does it make sense? That's a pretty large radius circle where we're at right now. And if we got further down here, does it make sense the radius of the circle is really not quite as big down there? So do you see why it's important that they told us we're at 2 meters? They said, where are you right now? Because there's a lot of circles, a lot of different circles on that parabola, if you will. So we know where we are. Well, again, I find myself thinking, I haven't even really read the question yet, but don't I have a formula that said that the radius of the circle that I'm at is equal to 1 plus the derivative. Notice this is a really nice equation to take the derivative. What's the derivative of 0.4x squared? Blurt it out. Not quite 0.4x. Yes, it's x, but what do you do with the 2? 0.8x. And what does the formula say I have to do with that? What do I have to do with that according to that formula? You're looking at it, it's on your note sheet. You got to square it. And then all of that has to be raised to the 1.5 power. But that's divided by the second derivative. So what's the derivative of 0.8x? 0.8. Just 0.8. Notice that's the formula for any radius you'd like to know. Notice it's still dependent on x. In other words, where are you? So as soon as we throw 2 in, then we're going to know the radius of the circle we're on right now. But if we went to radius of 0, we'd get a totally different answer. See what I'm saying? So this is the universal formula to tell you the size of the radius of the circle that you're on. Basically, it's taking a complicated shape like a parabola and just making a circle out of it. Isn't that kind of cool? So at x equals 2, what do I get if I throw 2 into that beautiful disaster? I get that rho is about 8.4 meters. Again, I'm just saying, hey, I got this formula over here. Why don't I just, since I can, why don't I just figure out what it said? So I'm going to write up here dy dx equals 0.8x d. Notice the weird language for this. The second derivative of that equation is written kind of strangely. F prime of x and f double prime of x is a nicer language for that if you think back to calculus. Just for the fun of it, because you can almost, like, I think you almost, let's see, you can do this in your head. At 0, way down here at the bottom, if I was right there, if I put 0 in for x, I end up with 1 to the 1.5 power, which is 1. I end up with 1 over 0.8, which is 1 over 4/5, which is 5/4. I get 1.25. So I'm up there on a big radius circle right now with a radius of 8. Whereas if you get down at the bottom, the radius is only 1.25. So you see how it's working? And isn't that kind of cool? We're not down at 0, but it's just something that's interesting to think about. So whatever, I know the radius circle I'm on. Now again, this is, do you understand how useless this is in a sense? Because what happens when the box is right here? You're on a new circle, right? You're on a new circle like 0.1 seconds later. So you can figure out what's going on at any given point in time, but it's not like you can figure out everything. You can just find out what's happening right there. Okay, cool. Maybe it's time to read the question. A box of negligible size. Sliding down a curved path. It tells us both x and y. We didn't need them to tell us y though, did we, right? Because we could have just put 2 into 0.4x squared and we could have found y ourselves, but I'm lazy, so thank you for telling me that. Notice they tell me the speed is v equals 8 meters a second. What does that mean? Well, in this case, it says when it's at a, that's its speed. So we actually don't know, unless they go on and tell us something about acceleration. We actually really don't know. So at least right then, that's the speed. And remember, that could be because you're a motorcycle and you're controlling the speed and you have it set to cruise control, or it could be because it's just sliding. And now we're a combination of gravity and physics and friction coefficients, which we'll be studying not too far from now. But does it make sense that velocity is tangential? It's pointing out of the graph, so to speak. So it's like 8 meters a second. That's the speed, at least right then. Again, I don't even know, like, do I need to know that? I don't know. Or we need to know that for. And it goes on and says the increase in speed. Oh, so it actually does have an acceleration. So this box has a speed, but it's actually speeding up, which if it was friction sliding down, you would think that makes sense, right? Because if it's sliding down something, it would be speeding up. Remember though, that's just the acceleration at point A, because as you move a little further, it's going to change. But the important thing is, what acceleration is that? What kind of acceleration is that? Is that AN or AT? It's not a direction change, it's a speed change. Didn't they call it dV/dt as if to, make sure we understood? They even said here, as I underlined, it's an increase in speed, not a change of direction. And they said dV/dt because it's a change of velocity. That's A of t that we're being told there. So there's a tangential acceleration and there's a velocity of 8. So finally, they say determine the magnitude of the acceleration of the box at this instant. Again, part of me wants to say it's 4. You already told me what it was. It's 4. But notice they said acceleration. They didn't say acceleration normal. They didn't say acceleration tangential. They're telling me the overall acceleration, which basically means I have to do that Pythagorean theorem thing. In other words, I've got to know AN and I have to know AT. Well, I know AT because I was given that, which is good because I never would have been able to figure that out any other way. So I'm going to also need AN. Well, how do I find AN? Well, I have that recipe that called for the speed and rho. And fortunately, we just got done figuring out rho was 8.4. And they gave us the velocity. And so, oh, that's cool. That's not bad. Did I get it backwards? Yep, I got it backwards. Thank you. So you end up with like 7.62. What's wrong with my units there? Yeah, feet per second, because it's, and again, just a side note, but if you put the units back into this, wasn't this feet per second? What's the unit for rho? It'd be feet. So I have feet per second squared times 1 over feet. Isn't that how you multiply fractions? So that means this foot would cancel with one of those feet. Oh, I'd be in feet per second squared. So if you let the units do your talking, that's great too. Question?
Isn't it all meters?
Oh, it's meters, isn't it? Thanks. Sorry, I got excited. Meters. So, part of me just wants to say, there you go. There's your acceleration, your accelerations. But if I look in the back of the book, that's not going to be the answer. The answer is going to be the Pythagorean theorem of those. And so just to draw kind of a picture of it then. Since we were told this was also 4 meters per second squared for acceleration, and we just discovered that this acceleration was 7.62. Incidentally, notice how much longer this vector, whoops, that's not right. Notice how much longer this vector should be than that vector. It's almost twice as long, so I didn't really draw that accurately. But as I said before, pictorially, the idea here is to redraw this 4, and this is actually the acceleration vector then that they're actually asking us for. So if I square those, add them together and square root it, then the answer I would see in the back is sort of meaningless as it might feel, is that. So the cool thing about 7.62 though is it's at least a number that's basically telling you what the pipe, the half pipe, so to speak, is doing to you. Does that make sense? There's this jump over at Mount Bachelor called the compression jump. I don't know if you've ever skied there before, but there's a cinder cone on it that people climb up, and you have to climb it. There's nothing that gets you to the top of that. You just have to climb it, but you need some good powder turns. But it literally is a cinder cone of volcanic origin. But there's a kind of a road on the regular mountain that cuts across the mountain, and because the road cuts into it, like roads, if you have a hill that looks like this, you have to cut a flat road into it. Does that make sense? But you can jump off of that. So first time I tried it, I jumped off of that and went ripping down the hill to the bottom where it turns up to the cinder cone. And I was surprised when I got to the bottom just to get thrown on my back. I mean, I just smashed my head on the snow because of the direction change, if you will. And so that was what the snow was doing to me. That number there is a reflection of what is that half pipe doing to that box? Well, because it's a box, it's not gonna change shape, as a result of that. But me, having to stand under my own power and musculature and so forth, it did change me. So, had I known that number, like knew what that would do to me, then you know, great, I could have done something different, but it basically collapsed my leg muscles. It's like I wasn't able to stand up against that much sort of direction change that was being required. And part of that was because the change at the bottom was really sharp. It had a tiny radius. Why would a tiny radius make that number so big? If you look at that formula, if the number on the bottom is smaller, that makes acceleration normal larger, doesn't it? So it made a huge normal acceleration because that radius was so tiny. Tiny radiuses are going to make you want to crash, and large velocities are going to want to make you crash. Does it make sense? Velocities on the top making acceleration normal larger, rows on the bottom, a small radius is going to make it larger. That's just kind of cool. Think about. Okay. I think we can live with that. Let me take a quick look at something else just to show you this. Let's see. I made something once before in Desmos for this, and I have just enough time to maybe show it to you if I can find it really fast. Sign up. I already signed up. We are all lovers of Desmos in here. Boy, I haven't been in here a while. The whole thing's different layout. There we go. Let's see. I have something in here called 12.7 dynamics. Ooh, this is the good one right here. So I just made this demo to model this because this is accurate now. This isn't me drawing a crappy picture, but so notice this is kind of like a skier that's coming down this ramp right here. So do you see the blue circle is the circle that they're on, and notice the center's located there, but I can move it, which is kind of fun. So notice the orange line represents the tangent. So that tells you where the acceleration tangent is aiming and where the velocity is aiming. So notice the smallest circle is right there, the tightest part of the radius. And notice over here, it's kind of cool because you see how it's telling me rho automatically. And I'm using, because I typed an equation of a parabola in here and I called it f of x, I was able to stick that rho equation in here and just say f prime and f double prime, and it did it for me automatically. I didn't have to make that for myself. I cheated, and so it's kind of spitting rho out there automatically for me. So I'm seeing a larger circle here, and visually it's just kind of cool to see. Notice how big this thing gets, because you're getting onto a pretty straight part of that parabola up here, and if I kept going up, it would just be larger and larger. So that's kind of cool. The other thing that I made in the past is this. Notice this is a crazy, what do we call that? If it's not solved for y, what's it called? Implicit. It's an implicit equation, not explicitly solved for y, it's implicit. And you may remember that we figured out how to take derivatives of that back in the day in calculus, even when it was kind of ugly like this. And so what's just kind of neat about this is notice as I'm kind of cruising along this, you're getting a picture of what tangent looks like, you know, as you're driving along on this weird curve. So what I would do if we had time is have you actually figure out what the radius of the circle is in all these different spots. Does it make sense to find the radius? We'd have to be able to take the derivative of that and take its second derivative, which would, you know, hurt us a little bit, right? Because it's been a while since we took calculus. But isn't it cool to think that despite the fact that this is a really wild curve, and you can imagine a road looking something like this, that you can actually, thanks to calculus and the science of infinitesimals, you could actually break that into infinitely many circles. And therefore, as you're driving along this, you could figure out how the curve is affecting you as a vehicle. So that acceleration normal is kind of a cool calculation. So we could take this road and sort of design around it. What I've noticed with mountain bikes is when you get up to a corner like that one I'm approaching over there on the right, I can't remember why I made. That's a really sharp corner right there. So they'll actually bank the corner up in mountain biking because you're gonna want to slide off the track. Does that make sense? If it's really sharp because you don't have the ground does not have the ability to kind of push you back to the center of that circle. So they'll mound it all up and make a nice big berm on the outside of it. That way you can kind of lean way over and just kind of roll around that, which in the berm is what's causing the normal acceleration, the capacity to kind of push you toward the center, which is what it's going to take to make the turn. And so the fact that you could actually calculate that radius right there, even though that's not a circle, and determine like what angle to bank that at, does that make sense? That'd be kind of, there's certainly a relationship there. The sharper the circle, the more I'd want to bank that. So this is really a powerful idea when it comes to really using this for something. And I'm always noticing that mountain bike trails, it's done by feel. It's done by people that have done it quite a bit, but they're not doing this much math because sometimes I notice it's not fast enough coming out of one corner to sort of hit the next jump, and they just haven't kind of built it quite right. And all this math would allow you to actually do that. So, all right, good enough. Let's see, I guess I'm posting these, so you're probably okay maybe not getting the blank copies of the two problems I did. So maybe, but if you do want them, I'm certainly able to give them to you. All right. Incidentally, on Tuesday, for some reason, this class did not record. I went in there to record the session. The only person I liked to Joseph. For some reason, it wasn't saved after I left the class. I don't know why. But hopefully today it will be, so I can post that.
The homework is just all the way up to 12.7.
Yes. Let me say one other thing about that too before you go, because it seems like, no, we're good there. Yeah, so in a sense, we're done with this week, and what I just showed you should get you all the way through that. So ideally Tuesday, or you can always email it to me, or emailing all that stuff to me, and then we'll jump into. And again, you should be reading ahead if you can, because now we're gonna look at what causes all this motion. That's what's next, and it'll be gravity and so forth that causes it. All right, see you all in half an hour.
My fiance helped me with it and she kind of lather glue all over the place. So it's heavy, but it has the paper on both sides. The only issue that I really have with it is that when it got glued together, you kind of see one side goes this way and the other side goes the other way.
Oh,
So it's
yeah.
not symmetrical.
So one side.
Yeah, flipped.
Yeah.
But
I actually don't think it matters because
I don't think it will,
I
yeah.
think they behave independently of each other.
Mhm.
Kind of like each truss does half the
So
job.
the only other thing that I did that was fancy is on the top ridge. It's an extra.
Oh, yeah.
So it's 45.
Yeah.
So
Were you here the day we tested them?
Mhm.
So you
So-
realize that that's kind of one of the weak points.
Yep.
So now basically, likely what would happen in your case, because you sort of have 3 of them up here, but only 2 down here.
It's gonna be
would
the
be
bottom
the
break.
bottom one would break.
Which I think would be cool to see.
I was gonna ask if you want to break this and you want to break it, we can absolutely do
Yeah,
that.
we can do that. We'll have.
Sweet, real quick. Be right back. Good for you. So if I remember right, I told you you'll have, I put 1 grade in the grade book, but what did I say?
It was just like retroactively
Yeah.
changing that grade and that.
It's gonna go from a B to an A, wasn't it? Or was it a C to a B?
I think right now,
I mean, I'll figure it out.
that specific assignment, I think I had half credit, so it was a 10 out of 20.
But I remember thinking it, I remember emailing you that if you did do this, your grade would go to the next grade.
I don't know, it might go, I know that I had a B in the class beforehand.
Yeah, I think it went from a B to an A, because I remember thinking,
Maybe.
I remember telling you like you should do it, because it's gonna change your grade, so. Rad, okay. I will make that happen. Thank you. Good job.
you doing here, Doug?
Hey, welcome.
Did you have dynamics?
Yep, I just wanted to let him out on time. Last time I kept him till like, I mean, I got that class, so this class right behind it, people gotta have a break.
Yeah. So I'm missing out big time on the dynamics. Pretty fun class.
We did projectile motion today. Figured out the velocity to fly the deer on a mountain bike to land in the right spot.
Right, we did a little bit of that. That is cool. I like that stuff.
Yeah.
You know, I have a buddy who his wife's, so his father-in-law used to work for some branch of the military as an engineer. He can't talk about it. I don't know what he did. But he said that at one point they were all working on a missile that would shoot up in the air and branch into like 10 different like sub missiles. And they had the accuracy that they could nail a dime anywhere on the ground. I was just like, oh my gosh, like, that's insane. And now he's like the CEO of New Calgon in Missouri, which is like an air conditioning business or whatever, I think. But still, he makes big money.
So,
Yeah, he's a genius. He's insane smart.
I imagine what that would take.
I don't know. And I was coming at it with like I was like in Calc 1 at the time, you know, with you first term. And I was like, I don't even know where to begin on what kind of math that would entail. Because we were doing like you say, like very sterile problems, very sterile stuff. And you're like, imagine if we put this into 3D, or imagine if like we added this element to it, which like was a realistic element. I was like, this man is doing the military where it's like a dime anywhere on the ground, those sub missiles could hit it. I was like, wow, that's crazy. So are we gonna be taking the strength materials test in classes soon?
Probably not.
No. Are we gonna do projects to fill the void?
I want to. I'm hoping to invent some stuff on the fly. Projects I do take a lot more understanding, and also a lot of tools. There's some interesting stuff, but it takes a lot of equipment.
Yeah. There's some cool stuff on YouTube with like presses and whatnot. Apparently it's like something people love is just watching stuff get pressed.
I also thought about field trips. I used to know, I don't now, but I used to know the lead engineer out of White City's Boise Cascade aggregate plant.
Oh, that'd be cool.
And I got him to take us on a tour. And their product is so proprietary, meaning they don't want anybody to know how they do it.
Why?
Because after a while, those patents wear out and other people copy it.
Oh,
Yeah, we had to sign things, you know, which is always funny to me because I had a bunch of 2.0 GPA high school
you did?
kids. And
Oh, you have these. Yeah.
it's like they're not in a position to like take anything in from this and go be different with like suits and ties and cell phones, taking pictures. But
For some reason I thought you were like, I graduated high school. I was like, no way. That's so weird because even if they are worried about that, I feel like Boise Cascade, didn't you say they had like the Bible of trusses and stuff like that? Like, even if someone could copy that, like no one's gonna even copy that whole trust Bible. That's so much information. I was thinking like how crazy, how many years it would have taken to like develop that. You know, that's a nutty amount of information. But they're worried about it. Probably found it.
not from this class is where it all comes from.
Yeah.
But I was thinking one of my favorite parts of that was watching a materials test. They have a little press that pushes down on like a 6-foot piece of it. It pushes down until it breaks, and they record, you know, how many pounds it broke at.
Yeah.
That's kind of their what's it called? Whatever whatever. It's just their way of making sure their stuff is coming out like it's supposed to.
Right.
But I remember vividly that it broke at double. It's sort of promised to break at, which
Yeah.
Stuck with me because I'm specing their products all the time.
Right.
Just to kind of think, okay, well, if I screw up a little bit, it's not like it's gonna break.
Yeah, it's not the end of the world. Yeah, on YouTube, people take those presses and they'll press like a can of like instant cheese. I forget what it's called. Like the whipped cheese or whatever. You just put it out of a can, and so they'll just see the can, and then after a while, and like cheese will just go everywhere, and people love it. They did like shaving cream. They've done basic stuff like watermelon or toothpaste, but like the toothpaste obviously it gets down really low, and the toothpaste just shoots out the sides. Like it's pretty fun to watch.
Yeah, get closer so you can see this, everyone.
Yeah, exactly.
I'd love to take you guys through there. I don't know if I could establish a connection again, but
Annie's dropping bombs on us today. I can sense that this class is going to get into like the theoretical, like, and I'm just like, oh no. That's one of my more least favorite topics of math is stuff I can't really imagine or picture.
spaces and eigenvalues. I haven't taught that class either. I'm not sure if I want to.
That's kind of, vector calc with Mary was a little bit like that, where it was like you were able to picture it, like with the help of that, I forget what it's called, not Desmos, but the other one,
Yeah.
where it's like a
GeoGebra.
GeoGebra. Yeah. So it was like a little bit easier, but it was kind of hard to like when you took unit vectors, like what you were actually doing and how you were manipulating it. It was hard to imagine that as you went along, but it was easy to imagine like, oh, this is what you're calculating this vector right here. But we're already kind of dabbling in, spaces where I'm like, oh, I'm kind of having trouble picturing what we're doing here. You know what I mean? And it's like day 2 of this class, day 3 of this class. So
Ask her lots of questions. She's really
she's awesome. Yeah.
sharp and will answer them. Yeah, the problem with that class is that if you go beyond 3 dimensions, at least in vector calc, you have things that can draw 3 dimensions for you.
Right.
But you just go on to 4, 5, 6, 27 in that class. So
Yeah.
it isn't a way to picture it.
Do you feel like what you learned in, because I thought, aside from like derivatives, I feel like derivatives show up a lot. This was going to be the most applicable class to the real world, like just taking boatloads of information and like condensing it into a readable, like palatable thing. So do you find that's kind of how for you is like the real world?
Yep.
All right.
And the important part from a practical perspective in 261 is just solving 10 equations, 10 unknowns, which is something you do right off the bat.
Yeah.
And you use technology to do it.
Mhm.
That's something you use a lot. I've heard, for instance, that the Golden Gate Bridge is the balance of 32 different forces. I mean, I can't even create that many forces. But,
Really?
I mean, I can think of the basics,
Right.
wind and cars and the weight itself, but seismic thing, if you,
Huh.
so where are the rest of them?
Yeah, I'm curious. What are the 32 forces on the Golden Gate Bridge?
I have some cool examples of that. I have 9 unknowns, 9 equations, 9 unknowns problem about the temperature distribution inside a dam, which I actually call dam math. Let's do some dam math.
No.
Linear.
Oh, linear? Yeah. That's kind of, I was talking to Doug about it, how linear algebra is probably like most of the real life.
I was thinking about that. She was even talking about this.
Yeah, well, she
I
kind of
mean,
like,
I guess it's not this stuff.
It kinda- yeah, she kind of like downplayed it a little. She's like, it's hard to like imagine scenarios in which you use this, but they come up. I was like, oh no, it's not hard to imagine. Like, I imagine it all the time, you know. But dude, you kind of missed her warning about how she's like, this class starts off like relatively easy. She goes, does anyone feel like this is like pretty easy? And a lot of people shake their head. She goes, at chapter 4, it gets hard, like really hard. It's like she goes, it gets very theoretical and hard to imagine. And she kind of has to like work hard to understand what we're actually doing.
Don't care.
Kind of hates that first test. Speaking of which, we're gonna have a test next week in this class too, don't we?
It's all true. It's not that far away in this class.
Do you test the dynamics?
What's that?
The dynamics too.
I think it's further away.
I remember linear algebra week 1 homework is due Monday, but week 2. Yeah. I didn't know what you meant. You stepped out to go to the bathroom or something before you left for dynamics. You missed something super important. It was one of those two things, whether it's the homework day or whether it was her warning of it's going to ramp up.
Oh, she already.
About to ramp up.
Fine, I can figure anything out.
Good to tell.
Sorry.
How's that going?
I like what she-
How really?
I woke up at 6 this
I can wake up at like, I do wake up at 5 for work, but for anything else, I like hate waking up early.
morning. I have to think, I have to like basically trick myself into staying awake up. Like, a lot of times, like I've tried many times to be an early riser and failed, but I've developed a system that's foolproof.
And tricking yourself.
I set my phone on my Keurig. I have it up under, ready to go.
Okay.
I have it all loaded. So the alarm goes off. All I have to do is press the button on the Keurig. It starts making my coffee. It's like once my coffee's made, I'm not going back to bed.
Wait, so.
So my alarm is. So I'm sleeping over here on this side. Like on top of my fridge on the other side of the room.
So you get up.
Nice.
So the alarm goes off, wakes me up. I go over to turn the alarm off, and it's on top of the Keurig. I'm like, oh, and I make coffee.
So you know what I would do? I'd turn my alarm off and then I would not press the key button and I'd go back to bed. Like I cannot wake up, dude. Because I know, like
It's called sleeping with shit.
dude, there's always something, right? There's a point of no return. Yours is making coffee. If that was my point of no return, I would be like, the second I press the security button, I have to be up, and I just wouldn't press it. Like, no, I'm not gonna do it.
Rad. Is your brain ready? Is that enough for a break? All set? Good.